So we're streaming. Hello. Um, Today I just want to do like very light work of um, Leetcode. I want to solve many problems, but easily. Don't really go deep. Just solve as many easy problems as possible. Um, all right. What's the easiest problem that I can solve here? Insert interval. Meeting rooms, insert interval, advanced graphs is not gonna be easy. 2DDP, I don't think this is gonna be easy at all, but oh, bit manipulation is gonna be easy. Go. Single number. Dark reader off. Given a non-empty array of integers, nums, every element appears twice. Non-empty array is a non-empty, appearing twice except for one. Find that single one. You must implement a solution with a linear runtime complexity. And use only constant extra space. All right, we have a vector. Only constant extra space. I think constant extra space, if you have a space of n, that's gonna be easy. I'm just gonna create a new vector of ints. All right, ints. And count for int I from 0 to size, obviously. Also implement that. Implement the solution. We're gonna iterate again. So if count I equals to nah, that's wrong. This is wrong. What if we have ones and we have two? Let's say no. Instead of count, we have ones, singles, and twos. We have singles and twos. So if this number nums I is in singles, and singles insert nums I. Linear runtime complexity. If singles find nums I, insert nums I. Else twos. Nums I and maybe so every element appears twice. So once we insert it in twos, let's remove it from the singles. And I think we will be left with singles that CVP set do we need an iterator here? Using iterators. Range space for a loop. Yeah. Did it erase? This worked, but it's hella slow. It's linear, but it's slow. What's that? What did I just click on? Complexity, the complexity here. Oh, okay. Single number. That description. Topics. Array bit manipulation. Bit manipulation would be interesting. Hint 1. Think about the XOR operations property. I think. So what's XOR? Let me just remove this stuff. All this shtick. Let me just remove all this shtick. And think about XOR. XOR means or, but like only one if well, in this case only one of them has to be sorry, caret symbol bitwise exclusive or. This operation compares corresponding bits and two operands. So essentially, if they are the same bit, they get set to 0. 5. This would turn out 0. I think this should just give me a 0, right? Endl. Call it Endl. Endl. Sealed Endl. Am I doing something wrong? Std 0. What's house end? How's or? How is or in C? Logic. Oh, I know or. It's so easy. Why did I miss it? Run. Std out was 1. Why would this give me 1? I don't get. 5 in binary. 5 in binary. 101. Should have just given the same number, no? If it's 1 on 1, 0, 0, 0. This is really odd. Why 1? This is very awkward. Why 1? Why? Or 2 ints. Two Boolean expressions and returns true if at least one of them is true. When applied to integers, converts them to Boolean values, where any non-zero value is considered true. This is just gonna output true. True. True is 1. Alright, true is 1. Yeah, 5 or 5 essentially was same as true. But what about this problem? I don't get why this problem is. Think about the XOR operations property. If we iterate over nums and set I don't get how. Tell me how. Tell me how. Tell me how is this good. Solution. Hint 1. A brute force approach would iterate through the array, checking each element using a nested loop. No, nested loop is bad. Otherwise, the current element is the required number. No, we use a hash set. Iterate through the array, adding elements that are not in the set, while removing those are already present. After the iteration, the required number remains the hash set. Oh, this is simple. I used 2 sets. I used a really bad thing. Well, I don't really need 2s anymore, don't I? Like, I'm not really used 2s anymore, so let's just essentially just kill the 2s. run again. This is good, but this is still slow. Singles, 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 singles. Wrong answer. No, that's it's 5%. There is something else in 3. Think about the bitwise OR. What is the result when two identical numbers are XORed? They are zeroed out. They are zeroed out. But how should I use this? When two identical numbers, they cancel out. 0. Since every number appears twice except for 1, the XOR of the entire array gives the number that appears only once. How? What do you mean? Sorting. This is what you mean. This is what you mean. And 0 and some number. Wow. This is an interesting proposition. This is an interesting thing. What if they are not in order? Like 4 and 1. They're not gonna cancel each other. This is gonna be probably some number. 2 and 1. This is also gonna be some number. 1 and these might be some number, but it will probably cancel out one speed. And 2 will then cancel 2 speeds here. So we will be left with 4. Now this solution is true if we assume that C equals A XOR C XOR B. How do we prove this? How does one evaluate this? I think this can be done using set identities. What? Fuck you. Fuck you. I think ChatGPT will know. How do you prove? Associative and commutative properties. Commutative. Oh, this is very easy. A, B, C. Just swap this. An associative means x to the y associative. this is cool. It's cool. So you can assume this, and you can prove this stuff. Right, let's just implement this. Int res equals 0 for int n in nums res equals res zor n. Return. And now it's fast. Now it's fast. Now it's fast like other smart people did it. How many times has this been solved? It has been liked by 20,000 people. So 20,000 people solved it. All right. All right. This is an easy grind. We don't do anything hard here. Number of 1 bits on Leetcode. Given a positive integer n, write a function that returns a number of set bits in its binary representation. Given a positive integer n, write a function that returns a number of set bits first to a bit in the binary 1. You mean once in its binary representation. Hamming weight. What's the Hamming weight? Hamming weight 4. Hamming weight 4. Hamming weight 0. Hamming weight 10. What's that? String of a string is a number of symbols that are different from 0. Okay. Oh, input binary 0. I think this might have a by 2. I don't know how to do this. I don't know how to do this. I think we should start by, now let's print out I actually don't know this. Let's print out. Well, easy thing is to print this in binary. And then how do we convert this thing to a binary? We have 11, right? 11 equals 8. We start with the biggest power of 2 plus 4. No, it can't be. Or next power of 2 is 4, but it can't be, because 8 plus 4 is 12. So it's 0 plus 2. Next is 2. And the next is 1. The next is 0. So this in binary, it would be 1 0 1 1 0. All right, 11 in binary. Let's just check this. In binary, 1 0 1 1. Wait, we don't. Yeah, I think we don't do this. We don't do this. We don't do that, because 0 would be just not 1. This is nonsensical. 1 0 1 1. This is 11. Now another problem is, how do we get closest power of 2? closest power of 2. This is... Now we have 11. How do we get the closest power of 2? Eight. So 8 is just 1, 0, 0, 0. Right? 1, and then everything else zeroed out. Can we cast this to a char? Is there some bit manipulation? Do we have some hints? Get some hints. Hints, guys, hints. No, this is 1 and 1. The given integer is 32-bit integer. Can you think of bitwise operations to iterate through its bits? Maybe we should consider iterating 32 times. Hint, we iterate 32 times, 0 to 31, using index I. The expression 1I, what's that? Bit mask with a set bit at the ith position. How can you check whether the ith bit is set in the given number? Maybe you should consider using bitwise AND. Oh, this is so smart. This is so smart. Here are our two powers of 2. Here are our powers of 2. 1, 2, 4, 8. This is great. This is great. So what this line does, it's gonna take this 1 and shift it to the left n times, which means essentially add 0 to the right. In this case, this would be shifted to the 1, this would be shifted to the 2. This is not shifted at all, so this is yeah, 0 shift, 1 shift, 2 shift, 3, da, da, da. And this is 8. Okay, so now how do we know that bit mask? Let's call this a bit mask. Let's call this a bit mask. How do we know that this set is set to, so, all right, if and every non-zero is true. So if and how do we say and bit mask? And bit mask is true. This means that the bit, the relevant bit was 1. So w weight equals 0, weight plus plus, weight plus plus, and return weight. No wrong. Ah, dang it. Output was 31. What? No, this is always gonna be 31 because this is wrong. This takes this int as a bool and this int as a bool, and they are both non-zero, and non-zero is like true, and true is true. So this is always gonna be true because int is cast as bool here. I need an actual boolean. How to do boolean int cpp boolean and boolean interdistinct type. Oh, bitwise and int cpp bitwise and this is good. This is good. This is good. Alright, we solved 2 problems. Easy. 2 easy problems. Counting bits. Let's go. Given an integer n, return an array n's of length n plus 1 such that for each I is the number of i's in the binary array of n's of length n plus 1 such that for each I once I is the number of ones in the binary representation of I. Are you going to do the same? How? It is very easy to come up with a solution with the runtime of n log n. How? How is this? Number of ones in the binary representation. I need a pen. I'm gonna draw this shit. Alright, I got it. Got a pen. So, whew. I to N. Let's say N is 5. N is 2. Alright. We start with 0, which is obviously 0. We add 1 to it. And I can't seem to come up with a solution then. Hint. Have produced already. Produced already. What I have produced already. Divide the numbers in range 2 minus 1 minus 1 and so on, and try to generate new range from previous. Divide the numbers in ranges like. Or does the odd even status of the number help? Right, if Alright, just tell me the fucking right up, man. Counting bits. Bit manipulation 1 inbuilt functions. It's about a bit manipulation. Vector of int res n plus 1 0. This is smart. I equals 1 1 there. So we're skipping the 0. We're skipping the 0. And if num equals I, well, num is not 0. And num minus 1. What? 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 Why are we doing this? Num and num minus 1. Ah, okay. Okay. So this trick actually works, but I don't know why it works. Um, oh, this is the same trick, but same trick. I don't think this will work. I don't think this will work because it shouldn't, right? The runtime is not n log n. Oh, it's n log n. Why is it n log n? We're doing 2 for loops. How big can n be? It's another problem. How big can n be? N can be a really big number. Then 32 doesn't really matter, I guess. Log n. Why does this work? This is easy. This solution is easy. This solution just builds up on the previous problem. But why does this work? So when you end a number with a previous number, right? something interesting that happens when you end the number with the previous number. Oh, this is also when you log in. Wow. So when you um I think I have a similar thought as to like when you have a whole number, well, like when you have a power of 2, it's only 1. It is only 1 bit. It's only 1 1, so to say. Uh, but the previous number, like power of 2 minus 1, is gonna have all ones. And yeah, I don't care. Built-in functions. Z and log n, bit manipulation, DP, dynamic programming here. Whoa. This is gonna be also a very interesting solution. We have count bits int n. We have vector dp n plus 1. We make a dp of n plus 1. Size n plus 1. Right? Offset is 1. What is offset? Offset times 2. I don't get what offset is, but let's say we have n equals 5. We're gonna have a dp of 6 elements. All right. Wow. We start from 1 index and go to the n index, which means we skip the first element of the dp array. If offset times 2 plus I. This is an interesting thing. How is this possible? Offset equals I. Oh, this is so fucking smart, guys. Look at this. So, in a way, you start with 0 and then you add 1. And once you have reached a power of 2, you again start from 1. And then you add like 1 to, you add another 1. And then you reach another power of 2, which has to be 1 here, you know. So this, in a way, oh, I can't tell you that I understand, but offset. You add 1 to the offset. So whatever offset is, offset is really the most recent power of 2. When we begin our loop at 1, our most recent power of 2 is 1. Recent power of 2. And then we go back to offset, to the offset, like go back according to the offset and add 1 to whatever was at that place. So let's say we are at I equals 9. The offset is going to be 8. It's going to be 8. So dp1, dp9 is going to be 1 plus dp1 dp1, 1 plus dp1, 1 plus dp1 was 1. So in a way, if you think about now, where was the example? God damn it. Like this. All right, let's start with numbers. Only 0, 1, 2, 3, 4, 5. And the count vector is gonna be 0, 1, 1, 2, 1, 2. See the pattern here? Is here offset is this, here offset is this, here offset is also this. All right, let's begin. Vector now we can prove this. We could prove this. Could, because we can't, but we could. Why this works? When you go to I-1 offset, it's the same set, it's the same bit mask, but it has one bit to the left in the bigger bit side. This works because of that. Essentially, it works because of that. Now, the base case would be dp0, which is initialized to be 0, and then we don't touch 0. Offset is, most recent power of 2. In the case of I equals 1, it's 1. Obviously, it soon becomes. So if I times 2 equals I, no, offset. Now, if new power of 2 is encountered, we actually set offset to I. And this actually builds the result vector, VP. Oof, that was interesting. Now let's also do the other solution, which is, all right, we have a result vector built in, result. What we're gonna do, we're gonna start iterating from 1 to n. I think that is correct. And while, all right, and int num is I. So while num is more than 0, num is gonna be ended to num minus 1. That's what's gonna happen. And int count is essentially gonna be 1, and count is gonna be increased every time. And once this loop ends, once num becomes 0, the result of I becomes count. This should work. This should work. Count plus plus. Runtime error, integer overflow. What? Oh, this has to be ended, not Zord. No, not wrong. Maybe it has to be 0. Now, why does this while trick work? Why does a while trick, this while trick work? That's a good question. This is a good question that we have to answer, honestly. I can give examples, right? Accepted. Is it accepted? Is it submitted? Now, when we have a power of 2 and we have the previous number, when we end it, when we end those stuff, it just becomes 0. This means we did only one end operation, and count plus plus gives us 1 bit. Let's say we have another number like this, and we have to end it with previous number. Obviously count plus plus. It becomes what? it becomes this number, and when we end it to a previous number, it becomes this. Becomes 0. So for some reason this trick works. 2 counts. Like, the thing is, say we have like a weird, like this pattern of ints. Ending it with a previous number, this is gonna be absolutely the same here, but this is gonna be to the previous number. So it takes away one bit, one set bit. Yeah. And this is gonna become like this. Again, ending it with the previous number is gonna be that, right? No. God damn it. It's gonna take away one bit, essentially. It's gonna take away this bit. Now we're left with this. 1, 2, 3, 4, 5. Again, a similar thing is gonna happen. Like ending with the previous number. It's gonna take away this number. So there are two cases. Is the last set digit what if it ended with ones? What if it was just like that, 2 zeros and 1? You end it with previous number, you take away this bit. If this is 1, if this is 0 and this is 1, previous digit is this. You take away. So I think the caveat is this. It works because bit and bitwise ending with previous int causes the last set bit to go away, to turn 0. So question becomes, how many of those set bits do you turn to 0 unless none, unless all of them are gone. So this, why this works, this is why it works. Damn, bits So still there is an improvement. Oh yeah, the improvement would be, this is bits. All right. In memory, it only beats 60% because another 40% use maybe dynamic programming. No, but no, dynamic programming also allocates. All right. Reverse bits. Should we do this? Hmm. Math and geometry, rotate image. These problems would also be important. Uh, Still, like I have done these problems, but I still need to practice them. Graphs. Da, 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 da. Advanced graphs. Da, 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 greedy. Jump game gestation. Insert interval. Merge interval. I need a lot of work, man. This is not enough. This is not enough. Right, that's for today's Leetcode. I will have to study other things because I'm studying at university. So I have to go. If I didn't care about my university or if I didn't care about other stuff, I will do more Leetcode. And I think I will, actually, because I don't give a damn about. And what else do I have? You know, university assignment will be done in 1 week, and then I'm doing nothing, I guess, essentially. So, yeah, we'll probably meet today with more problems and more harder problems.